Okay, so we're talking about electron delocalization. We've seen in the last video, if we have, you've got ethene on the left there, and so if you the red orbitals, these are overlapping to form the sigma bonds, and we have an unhybridized, unmixed pair of p electrons on that carbon. And what happens, as we know, is those unhybridized p electrons, they overlap to form the pi bonds. So they form that. There's our pi bond. Okay, so we're going to get electron density above and below the plane of the molecule. Now let's look at this one. We talked about this one, butadiene, and again we've got unhybridized p electrons here, and here, here, and here. Now there's nothing. The distance between these two carbon atoms, number 2 and 3, is the same as the distance between 1 and 2 and 3 and 4. So what happens, you don't form two discrete pi bonds, you form a big delocalized system, which I'll try and draw, which will look something like this. So you'll have one thing above the plane of the molecule there, and you'll have another one below the plane of the molecule there. And that is a slightly more stable arrangement than if there was two separate double bonds, because the electrons can spread out more, and that's called delocalization. Now we look at benzene. What we've got with benzene is we have got 6 carbons in a hexagon. Okay, and we have got, if you think about a regular hexagon, you'll probably know that the bond angle in regular hexagon is 120 degrees, the internal bond angle, which is exactly the bond angle you should get when a carbon is forming 3 bonds. So benzene will be a completely flat structure. All of those carbons are in the same plane, that all of those bond angles are 120. It's a completely regular hexagon. Okay, so it's a nice flat structure. So let's draw benzene, draw it side-on view. So here's our carbons. I'll draw these with a bit of depth in to show that we're looking at it side-on. Okay, and this is flat. So I do my usual little thing to show it's flat, a piece of paper. They're all fitting on that piece of paper, flat. And we have got p electrons on every single carbon, because we're forming alternate single and double bonds. Don't forget that's what we're saying, alternate single and double bonds. So each carbon has got unhybridized p electrons. Okay, so they don't form 3 separate pi bonds, they form a whole delocalized system. So it shows that what actually happens is, oh, is it going to let me get rid of these? Yeah, there they go. Right, so you end up with a big ring on the top there of delocalized electrons, and another ring underneath of delocalized electrons. Okay, so that's what benzene looks like. And usually, don't forget the hydrogen sticking out on each carbon, 1 hydrogen on each carbon. So quite often at A-level, we draw the benzene like that to show that the electrons are delocalized. Now, this, for a long time, people thought that it was alternate single and double bonds. And the first person who proposed this was called AQA, and so this is called the AQA structure. He was because they knew the formula was C6H6. Okay, so that is, if you look at the ratio of carbons to hydrogens, that's very unsaturated, and no one could quite work out what was going on. Then he proposed if it was a cyclical molecule, that would explain things. So we call it the AQA structure, which doesn't exist except in our heads. Okay, and this is the real structure. Okay, now there's some thermodynamic. Well, there's various evidences. Okay, so we'll talk about evidence that the of delocalization. Right. So one, all the bond lengths are the same. In benzene, they're all the same length. If this was the structure, you've got alternate single and double bonds, and double bonds double bonds are shorter than single bonds, and so you'd expect not every bond to be the same length. You'd expect a short one and a longer one. Also, if you look at the bond lengths are intermediate. They're intermediate between single length, which is short, and double, which is longer. So that's another bit of evidence. But what we're going to look at now is thermochemical evidence, so enthalpy experiments, okay? So thermochemical evidence. Okay, so if you have hex 1-ene, okay? So here's hex 1-ene. And you react it with hydrogen. You turn it into cyclohexane. So no double bonds there. And that is exothermic, and you get out minus 120 kilojoules per mole. So you would expect then, saying if we had the AQA structure, so I'm going to draw here, and it really was alternate single and double bonds. And you reacted that with 3 moles of hydrogen to form cyclohexane, you should get 3 times minus 120, which is equal to minus 360 kilojoules per mole. That's what you'd expect. But you don't get that. So what you actually get, and this time I'll show it, is this is the real benzene. This is what it really is. I might put that in inverted commas to show that it doesn't really exist. There's our real benzene, and you react that with hydrogen. You do get cyclohexane, and it is exothermic, but you only get minus 208 kilojoules per mole. You get less energy out than you would expect. Okay, it's not as exothermic, so that suggests that this is more stable. And we can show this on a little energy level diagram, like we've done. If you've done the Born-Haber cycle already, you'll be aware of this. So if we just have we put energy here. Now I'm going to put cyclohexene here. And hydrogen. And that line is to show the energy level. Okay. And then if we react it to form cyclohexane, it's exothermic. So that means the product is more stable. So the product is going to go down here. So I'll draw the product here. Cyclohexane. Right. And now the energy you get out for that, we've said, is 120 kilojoules. So let's put our AQA structure up there, which doesn't really exist, of course. The alternate single double bonds. So we would expect if we reacted that with the hydrogen, okay, you would get 360 kilojoules per mole out. But we know if you do the experiment, you don't get quite as much as that out. So I'm going to draw, this is the Kekulé structure, not the Kekulé structure, the real structure of the delocalized. This is what you actually really do get. You only get 208. So that means the benzene, by the electron delocalization, is stabilized by that much energy. So it's stabilized by, what is it, 360 minus 208 by that many kilojoules per mole. So you can see, right, benzene is it's not such a high energy state as the Kekulé structure, and that's because the electrons are delocalized and the electrons can spread out then. Right, just before we finish up there, I'll just give a couple of, they have asked a few questions on this in recent years. Right, they've said, right, right, you've got cyclohexane, and you've got this diene, okay, and you've got another diene where they are like that. So the energy you get out, and then, well, let's draw benzene in there. As well. Right, so if you react that with hydrogen, you get minus 120 kilojoules per mole. If you react this with hydrogen, with 2 moles of hydrogen, they say, what would you get there? Now, are those electrons, can they be delocalized? Well, you've got unhybridized p electrons on that one, and that one, that one, and that one. You've got a gap there of 2 carbon bond lengths. And as we said before, that means that those 2 separate pi bonds can't mix together and form a delocalized system. So there's no delocalization there. So you'd expect the value for the reaction to be double the one with 1 bond. Now with the benzene, we've said before, yeah, you do get delocalization. So you react that with 3 hydrogens. With the benzene, you do get delocalization, and you only get minus 208 kilojoules per mole. So the question is, what do you think you'd get with this one? Right, you do get delocalization here, don't you? Because those p electrons and those and those and those, they're all separated by, there's only 1 carbon length. So those 2, they will form one, they won't form 2 separate pi bonds. So you're not going to get as much as 240. You're going to get slightly less than that. And that's the exam question. And I think they accepted various answers, but let's just, I've got a calculator. Right, so I think the way it's going, first of all, how much you're going to get. I think if you say anything, you're going to get less than, less exothermic, okay, than 240. So you're probably going to get something like, I don't know, 190 or something like that. I suppose what you could do is divide 208 by 3 and then times it by 2. If you do that, I think you get 140 kilojoules per mole, something like that. I think anything above 140 and less than 240 got you the marks. But it's just to understand, really, you will get delocalization with this one, but you do not get delocalization with that one because the bonds are, they're not alternate single double, they're separated by more than 1 carbon bond length. Okay, so that's how benzene is more stable than you would expect it to be. and that affects its reactivity. We'll see in the next few videos, but just before we move on, so how do you test for a double bond? Well, you test for a double bond with bromine water, yeah? Benzene will not decolorize bromine water. Okay, and that's because the it's too unreactive because you got electron delocalization. So benzene, generally speaking, what kind of a reaction is it when bromine reacts with that? It's an electrophilic addition. And we'll see that benzene doesn't undergo electrophilic addition reactions because that would entail breaking the delocalized system. So we'll talk about that in a bit more detail in the next video.